So let's do this example from the textbook. I don't think it's listed in the slides. I think that was just an error on my part. I forgot to include it in the slides. But let's do it here. And it's some practice with converging lenses and the characteristics of the image formed by converging lenses. So just as a quick review, right, a converging lens is a lens that is thicker in the middle than it is at the ends. And a converging lens, we kind of draw, right? A converging lens is made of two spherical surfaces, right? If this is the first side of it, lens one, and the ray is incoming on the left, the radius of curvature of this guy, this left lens, the first lens, is going to be over here, right? Because that would be the center of the sphere that creates that lens. So we'll call that R1. So if the radius of curvature is on the outgoing side of the ray, the radius of curvature is on the outgoing side of the ray, then the radius of curvature is positive. Okay, so for converging lenses, the radius of curvature is positive. So this is the summary, the sign rule summary in the end of the chapter that you might find helpful. And it summarizes the sign rules in a general way for mirrors and lenses. And to summarize it for both mirrors and lenses, you have to define the positive or negative radius of curvature in terms of the incoming and outgoing side of the surface, okay? And so for a mirror, it's very easy to understand what the incoming and outgoing side is, because the incoming and outgoing side of a mirror is always the left side, right? The incoming side, and then the light reflects and outgoes on the same side, right? But for a lens, the incoming side and the outgoing side are on opposite sides of the lens, right? Because lenses allows the light to pass through it. So the ray is outgoing on the right side of the lens. And so for a concave or a converging lens, the radius of curvature that belongs to this side of the lens is on the right and therefore is on the outgoing side, and thus R is greater than 0. Okay, and in the next example, 3410, I will show you an example of a diverging lens. So, but now I'm just kind of showing you why R is greater than 0 and how to interpret these sign rules from the summary in terms of a lens or a mirror. So now that we've established that the radius of curvature is positive for a converging lens, let's do this example. We're not going to do, don't worry about the radii diagrams. Let's just do the math, okay? Let's just do the math. So we are asked to find the image position, S prime, and the magnification, M, for an object at each of the following distances with a focal length of 20 centimeters. All right, so for part A, S will be at 50 centimeters. Okay. Part B, S will be at 20 centimeters. Part C, S will be at 15, and then D, S will be at negative 40 centimeters. Okay. So we're going to use the exact same object-image relationship from mirrors. Same thing applies to lenses. So we can do either 2 over R or 1 over F. We'll go ahead and do 1 over F. All right. And so we are given, so we want to find S prime and then find M. Okay, so let's find S prime. So we're given the focal length, which we know is positive because we're dealing with converging lenses. So that's going to be 1 over 20 centimeters equals 1 over the unknown plus 1 over the object distance, which in part A is 50 centimeters. So our 1 over S prime is going to be 1 over 20 minus 1 over 50. Okay, it's going to give us a negative. No, it's not. It's going to give us a positive number because 1 over 20 is bigger than 1 over 50. And that gives us 0.03. So that means S prime is 1 over that. Which comes out to be 33.3 centimeters. What is the magnification? So the magnification is, again, just the ratio of the image distance to the object distance with a negative sign. So we can quickly figure out the the magnification. Okay, and then the object distance was 20 centimeters here. So it's 33.3 divided by 20. So that is the magnification. Okay. So, it's negative, of course. The magnification is negative, which means the image is inverted, okay? So for part A, if we were to draw the ray diagram as I'm sure if you look in the example solutions, it will have a picture of the ray diagram, and you'll be able to see the picture that goes along with this, right? We're gonna have an inverted image, and the location of that image is gonna be 33.3 centimeters away from the mirror, which will be the lens, which will be to the right of the lens, right? And the real space of the lens. Because when the object distance, when the image distance is greater than 0, the image is on the outgoing side of the surface. It produces a real image. And for lenses, the outgoing side of the surface, that's up here, right? That's this side right here, which is the real side. Now, what about a mirror? Just for fun, right? The real side of a mirror is the left. Because, right, we expect light to reflect off the mirror and be on the same side as the mirror. The virtual side of a mirror is behind the mirror, where the light rays don't actually physically go. Right? The light rays reflect off the surface of the mirror and come back out. But for a lens, we expect the light rays to go straight through. Okay? So the real side is the right side of the lens, and the virtual side would be if the image somehow ended up over here on the left, which does happen. So let's now go to part B. So now we are placing our object at 20 centimeters. Okay, so our object is at 20 centimeters. Remember, our focal point is also at 20 centimeters. So what kind of image do we get if we place our object at the focal point? Well, you'll see mathematically real quick what that ends up being. Okay, 1 over S prime is 0, which implies that S prime is infinity. So your image ends up at infinity. It diverges. It's basically, there is no image, right? If the location of the image is at infinity, essentially there is no image, right? So if you were to place your object at the focal point of a lens, you won't get an image. So the magnification will also be Well, let's see, where does that math take us? You get infinity over a number, which is infinity. Okay, magnification is also infinity. So now we're slowly bringing our object closer and closer to the mirror. To the lens. We're dealing with lenses. So now for part C, the object is now inside the focal point, between the focal point and the lens. Okay? So our focal point was 20 centimeters. We're solving for the image distance, and then our object distance is 15 centimeters. So now you'll see we're going to get a negative sign because we're subtracting a big number from a small number. And so we're going to get negative 1 over 20 minus 1 over 15, 0.0167, which implies that S prime is 1 over that value. And so S prime is going to be 60. Negative 60 centimeters. Okay, so S prime is now negative. Okay, so what does that mean? S prime is negative when the image is not on the outgoing side, when the image is on the incoming side. Therefore, it is a virtual image. And so virtual images in lenses occur on the incoming side, right? Not on the outgoing side. So on the virtual side is over here. And so when we place our object, right, here's the other focal point, same distance away. So now we have our object inside of the focal point, between the focal point and the lens. That's going to produce an image that is virtual way back here. And let's see if it's upright or not. So we can tell by the magnification whether or not it's upright. And so the magnification, so we have negative of a negative. Okay, 60 over 15. That is, I believe, 4. Should know that because of a clock, right? So that's positive 4. So it's upright. It's upright and it's virtual. So part C is basically saying when object is placed inside the focal point of a converging lens, the image is virtual and upright. Okay, so that's basically, on an exam, these are the kind of questions you're going to get. You're going to get a converging lens, a diverging lens. You're going to get a spherical mirror, convex, a spherical mirror, concave. Characterize the image created by these lenses and mirrors, given object distances. Okay, and these object distances, and when you compare them to the focal length, you can get some commonalities here. So for example, like this for part C, for a converging lens, if the object is placed in between the focal point and the lens, then you're going to get out of it an image that is upright but on the virtual side of the lens. Okay, and so part D brings us negative 40. Okay, so let's kind of play with that. What does that mean? So for part D, we're going to place our object at negative 40 centimeters. What does that mean? Well, let's look at our little summary here. So if an object is negative, okay, if an object distance is negative, that means the object is not on the incoming side. It's on the outgoing side. And the outgoing side of a lens means it's on the right. So what negative s equals negative 40 means is that we're placing our object all the way over here, okay? And the question is, what kind of image are we going to get through the lens if we actually place our object on the outgoing side? So let's do the math to see that. So we know our focal point, our object image relationship, okay? So that's 1 over 20, solving for s prime, and then 40 centimeters for s, negative 40 centimeters for s. So now when we solve for s prime, that's 1 over 20 centimeters plus 1 over 40 centimeters. And that's going to give us, we can definitely do mental math to figure that one out, but I just don't feel like doing that right now. So that gives us 0.075 inverse centimeters, which means that s prime is 1 over that. And that becomes 13.33 centimeters positive. So that means our image is going to be positive, which means it's on the real side. Okay, so that's s prime. Yep, that's s prime. Look right here. Oh, you can't see that because I wrote in black. S prime is positive, which means the image is going to be on the outgoing side of the surface, which is the real side. So the image will also be on this side. Now, will it be inverted or upright? We can figure that out by doing the magnification. So we get a positive number, so the image will be upright. And shrunken. Okay, so image is upright. Image is real. Because it's positive. All right, so that is our example for a converging lens. So we calculated the image distance and the magnification for 4 different positions of the object, bringing the object, first we're beyond the focal point, and then we're bringing it closer to the focal point, inside the focal point, at the focal point, and then finally on the putting the object on the virtual side, which is what we did in part D. So we kind of cover all the cases, okay? And so then we'll do one more example with diverging lenses after this.